welcome to the VisGraph seminar. Today we have a special guest from the Europe, and Rafael this is going to introduce him, and then we start the talk. So take it on, Rafael.
Okay, so today we have here George, who just finished he got his master's degree in the TU Delft, the technology of University Technology of Delft in the Netherlands. And in the we had many talks in the beginning of his research in his master's, and I'm eager to hear what he accomplished. So it's a pleasure to have you here on our seminar today, George, and thank you for accepting the invitation. And so it's all you now.
Thank you, Rafael. That was a lovely introduction. So I'm here to talk. I'm very excited to talk to you guys about the three flatland problem. Before we dive into the problem, let me further a little bit elaborate. So as Rafael said, I'm George Edouin de Menibus. I did my bachelor's and master's in computer science at the TU Delft, and I completed my master's thesis under Professor Dr. Ricardo Marroquin, which is what we're going to be talking about today. I'm now a software developer engineer at AWS, but that is very unrelated to what we're working. So I've told you who I am. Now let me tell you why you should listen to me. And this is very simple, right? You want 100 times faster sampling, 20 to 30% faster renders, support for focus queues, right? All of these things and more. This is what you can expect to learn and to see in this presentation, right? And this would not be possible without the help of all these fine people who have been there at every step. So I think it's very important to give them all the shout out. Now, let's actually begin our story, right? This begins about 10 years ago. I was in middle school, and we get this, I saw this article in Wired magazine that came in my school library. This kid is about to change gaming, movies, TV, music, design, medicine, sex, sports, art, travel, social networking, education, and reality. The Oculus Rift is here, and it will blow your mind. It was, I think, as Jaron Lanier put it in his autobiography, the dawn of the new everything. This is the promise of virtual reality, right? A new kind of computing, a new way of interacting with the world. And if you look online, you'll see all of these pictures of these like advanced graphics and all this. But this article came out 10 years ago, right? Where's the future? Why are we not all, in this call with our VR glasses doing some kind of telecommunications and all this? And the truth of the matter is that article might have been a little bit too eager, right? VR, like all of computing, finds itself constantly having to make trade-offs between compute longevity and independence, right? There is this inherent tension that as researchers and engineers, we are constantly trying to fight against, right? And what we're mostly interested in is, if you remember those graphics I just showed you, they all have these kind of 2D images, right? Because 2D is a great way of conveying information. And yet somehow we still have to do this like longevity, compute independence. Intuitively, 2D feels like it should be kind of cheap. So let's explore a little bit what I mean by these 2D terms, right? This is a screenshot from a video game, Abiotic Factor. I'm a big fan. And here you can see that there's this like little UI element, right, that says elevator to fog. It actually occupies like 3D space. Or what I mean by that is, if you turn your head, it turns away, unlike the rest. If you move, it moves. If you look back on it, you can see it, right? And this is very useful for like positioning yourself in space in relation to other things, right? Which is a lot of information is enhanced by not only its position in the view space, but also its position in the real world. So let's clarify a little bit what we're working with. This is a very simple idea. We want some kind of head-mounted display. We want to have a real world, and we want to project some kind of 2D head-up display UI element, right? So here I've labeled an airplane. And intuitively, you might think, oh, okay, why not just go at this like a simple stereoscope, right? That gives us 3D, just put some kind of label. And the challenge is that just doing that gives us kind of some problems, right? The big problem is it makes us sick. And it doesn't just make us sick, actually, it makes us cyber sick. The reason for this has to do with the human vision system. So obviously, in order to do proper 3D, we have to induce stereopsis, right? Which has binocular depth vision, right? But also has monocular components such as parallax and optical flow, right? This is kind of what or at least binocular depth vision is what the stereoscopic approach brings to us, right? But in order to fool these other systems, we need to go further, and we need to do more than just displaying the image. Another system I have not mentioned, but is actually just as important, is focus cues, right? So just to define our terms correctly, parallax. It comes from the movement, right? As you move from different viewpoints, you see how objects move in relation to each other. Optical flow, comes from the movement of objects. Pretty simple. But focus cues for AR are particularly tricky because we are competing against the real world, right? In AR, with this see-through display, there's going to be a whole world of perfect focus cues. Which means that we're going to run into divergence accommodation conflict. So what is this? Well, this is a very, very simplistic representation, but here we have an eye looking through some kind of display, and we have on it let's say a picture of a monkey, right? And the monkey physically has to be on the panel, right? Like there's no other place for it to be, but we want to make it appear as if it's far away, right? In virtual space. The problem, in order to correctly identify depths, we expect a certain amount of blurring, or rather our brain expects a certain amount of blurring and correction, right? So, but the challenge here is that we're projecting the object as if it were far away, but we're providing only one focus cue, or only one place to focus, notably the panel in front of you. And this can create a lot of malaise and nausea, and it just makes this a bad experience for our end user. So in order to tackle that, we need to dive a little bit into the world of 3D. Importantly for us, if we want to account for multiple for focus cues, we need to go beyond treating the eye as a simple eye box, or as a simple pinhole camera, right? And evolve towards an eye box, and understand that our eye can take a multitude of positions within the socket, and in multiple and focus on multiple objects, right? So what techniques are available to us for tricking the brain, given that we cannot rely on just the pinhole camera? Well, the first thing we could do is we could use eyewear. Okay, this is kind of the oldest approach, and we will be using this for stereoscopy, of course, but it doesn't answer our previous need. We could use parallax barriers, right? And parallax barriers, have their uses, but they don't really fit our use case. And it's the same for holography, right? We want augmented reality. We want some kind of wearable display. Holography, very good at one object. Well, we also have light field displays, and light field displays are very interesting because they allow us to support multiple observers, right? Okay, that leads to the question of what is a light field? Because we care about multiple observers because we need to account for multiple eye positions, but how do we do it? A light field is a fifth-dimensional construct that captures all light in a scene, right? It can be described as 3 dimensions for a position and 2 dimensions for angles, right? And this sounds very intuitive. This is the definition of practically any ray in a scene. So what can we do with light fields? Well, the multiplicative approach to light fields is you set up 2 panels, right? And because different observers are going to see different combinations of pixels, you can kind of control what each observer is going to see, right? Additionally, previous research has been able to use this to develop head-mounted displays, though that was 10 years ago, and it was only for virtual reality, because at the time, LCDs did not have enough transparency to be used for augmented reality, and OLEDs had not rolled around and gained as much popularity as they have now today. There is also a newer additive approach, which is very interesting, and uses some holographic optical elements. But the challenge with the holography is that it takes slices of the scene in order to recreate that kind of 3D effect. And we're dealing with exclusively 2D content. So there are additional challenges that this would impose, and we haven't even explored if limiting ourselves to 2D content is worth it, right? There is some research into 2D HUD content, but it's much more interested in the projections and the mirrors and not optimizations or questions regarding how to solve this problem as efficiently as possible. I say this problem, but what is this problem? Let's dive in. Let's enter what I've called the 3 flatlands. So the 3 flatlands are composed as such, right? You have your 2 panels, right? Because it's the minimum amount of panels you need in order to use light field displays. And you have some kind of target texture off in the distance. And you want to figure out from given the target texture and positions of multiple observers, what content you need to put on panels A and B such that observers will perceive T. All right. What does this space already tell us? Well, compared to our 5th dimensional problem space, we're now down to 4 dimensions, which is very nice, right? In the sense that all rays in the scene must intersect with both panels and therefore can be described as 2 dots or two points on a plane, right? Hence 4 dimensions. More importantly, this work focuses on the discrete space, and therefore we have a limit of how much we can approximate the light field because imposed on by the granularity of the pixels. So here I have an example of a light ray that goes through 2 pixels in both panels and ends up in a wildly different position than the closest estimate that we can do. So let's begin by a brute force approach, right? So you have these 2 panels, right? And you want to say, okay, I need to consider all possible panel combinations, and with this, I will sample the entirety of my light field. And you do this, and you call your friend over at a department of machine learning somewhere, and he tells you, well, you know, there's actually a really good technique for this. It's called non-negative matrix factorization. All it does is, you know, given a target matrix, it can decompose it into 2 constituent submatrices, or in our case, 2 vectors. And this sounds really nice. It does exactly what we want. It's even non-negative, which is a constraint of our problem. However, it scales incredibly poorly, right? If we have 1K per panel and 1K target texture, we're going to use 4 terabytes. Okay, perhaps the memory footprint is bad, but maybe the results are good. The results are also pretty bad. And this leads us to our first kind of revelation, which is that not all rays are created equal. We don't actually care about every ray. A lot of rays wouldn't even hit the eyes, right? So let's delay the problem of ray selection, and let's say that the ray selection has already been made for us, right? How can we reason about the space? Well, we know that because we're going through 2 mediums with our ray, light in this case is multiplicative. So a light ray kind of imposes a condition on us, which is that the product of the pixels it goes through must be equal to T. We can extend this to this notation to be more flexible by introducing this mapping vector, right? And now we can reason about the totality of the pixel space and the totality of the target space, right? We can actually expand this idea and create these incidence matrices, right? That map a ray to a specific pixel. So here I have a representation of these panels imagined as one-dimensional. And from this, we can create a target function. From that target function, we can use an alternating update rule. The intuition behind this is actually relatively simple. If we were to substitute all mapping matrices with the identity matrix, we would get this update rule that I've got here on the right. And essentially what we're doing is a kind of a gradient descent, right? Because A element-wise B is our approximation for T, right? So we're using the approximation to guide our direction. Okay, so let's go back to our previous example, and we still have a massive memory problem. Now, we can solve the memory problem by using sparse matrices, because now that we've gotten rid of all the rays we don't need, most of the matrix is actually empty. And what's very nice about this is that the results are now looking good. What I mean by that is we can now see the monkey, right? Because we're in this scenario here, I've only sampled rays coming out of the monkey. So, but can we do better, right? This is no different. Here we're not yet leveraging the 2D content, right? This is no different than previous approaches in light fields. So let's go back to our theory, and let's maybe there's something we can figure out here. Well, there's these two angles that we've talked about, and it would be really nice if we could work with them and do something with them. And we can actually. We can discretize these angles and we can capture them. This is, not too dissimilar to how you do ray tracing, where you put a grid at a certain distance and shoot rays and then use the rows and columns. And this will let us reason about each of the dimensions independently, which means that we can avoid a lot of work. What do I mean by that? Let's introduce a new representation. This time, we've split the incidence matrix between the rows and columns. And when I say rows and columns, I mean the discretized version of the two angles that we talked about previously. By introducing this split, we are able to notice an interesting property, which is that this purple ray, right, as far as the red matrix is concerned, the purple ray could be substituted for any of the blue rays, and it doesn't matter. And as far as the blue rays are concerned, the purple ray is a stand-in for all of the red rays. Okay, this is unusual, but what can we use this for? So here I've represented similar scenes, one with the previous 2D view, and another with our new 3D view. What we can, by building the same mapping matrices and computing the result of the vector and the mapping matrix, or the matrix and the mapping matrices, we notice that there is an unusual discrepancy between both methods. And that is that the second method, right, where we split the rows and the columns and we reason about them individually, as in we make mapping matrices, somehow has captured A5 without ever firing a ray to it, right? And the reason is because A5 is, in some ways, the row of A5 and the column of A5 have already been sampled, right? And so this already is an interesting property because it allows us to sample actually incredibly quickly, right? Instead of having to sample the totality of the ray space, we only have to sample one column and one row. That's already very nice. Now, this leads us to a new update rule. It's the same thing as the old update rule, except now it takes into account the two different matrices. So despite that, something is missing here, which is that I talked about this ray separability in these two angles, but I actually played a little bit of a sleight of hand on you, because X, Y, and Z, assuming we're firing rays from the same position, remain the same, right? And therefore we can just think about rows and columns. But as soon as we start thinking about multi-view, this is no longer true, right? Two rays from two different observers who hit the same row and the same column should not be treated the same, right? And therefore, so the first approach is to just extend the ray space, extend the column space, right? So if there are multiple observers and we're firing 300 rays per dimension, right? To say, okay, now that there's a second observer, we're firing 300 rays twice, right? So 600, right? Or 300 rays 3 times. The problem with this is that the space grows really quickly, and adding observers will quickly overwhelm our sparse matrix, as we will end up with these massive matrices that do a lot of redundant computations as they compare rows from one observer to columns of another observer. And they compute this, but they never actually use this result. So this is very inefficient, right? So the question now is, okay, we want to maintain that row and column separability of the rays, but we have to deal with the multi-view and the fact that multiple observers can share rows and columns, so to speak. So what do we turn to? The answer is we just have to do more, right? We want to go from X and Y, as in row and column, to XYO, row, column, observer, right? That's what we need to think. So we have to find some way of having multiple viewpoints, solving for those viewpoints, and combining all of the results. And fortunately for us, this is where tensors come in, right? Tensors allow us to express more than matrices. And from these tensors, we can create mappings, or we can create transformations and projections, which allow us to capture the observer as a dimension. So we've gone from theoretically 5 dimensions to then 4 dimensions when we introduced 2 panels, and now we're down to 3 dimensions because we've collapsed the XYZ into this observer dimension, right? And this is actually really, really fast, excitingly so. And then we can create new update rules that use these tensor transformations to go from ray space to content space and to calculate our results. From this, there's still a couple other problems that are left open that have not been answered in prior works. The first one is the what I call the polysemios problem, right? Right now, pixels that are not sampled, right, because we're now doing ray selection, pixels that are not sampled default to black because black is the 0 value. And because of the methods we're employing, zeros appear because we're trying to minimize span. That's unrelated. So the question is, how can we distinguish between pixels that are void, as in pixels that have not been sampled, and pixels that should be black? And here we can reuse the matrices because the matrices tell us a row column combination that has been active, right? So now that we have a way to handle row column combinations that were active, and now that we have a way of having transparency in our displays, we can finally address the proper blurring and the treatment of the eye by just taking each eye position and placing a convolution kernel for sampling, right? So we consider multiple viewpoints for each eye. So what does this look like? Here we have an image of a sign, and if we run our approach, we get something that looks a little bit like this, right? So the people are still visible, but there's this kind of blur around them. And if we move the camera, you'll notice that the image has been decomposed over both panels. What this allows essentially is it allows the eye to focus on 2 different planes and give you a different level of blur. Okay, I've showed you the results. I've talked about the math. Let's move on into the nitty-gritty, the implementation, the measurements, the takeaways, all of that. This is a chart of the architecture. All of the things in red were run on the GPU side. The things in blue were run on the CPU side. The GPU was written, the GPU code was written in WGPU. The CPU code was written in Rust with the Fire library. Rust was picked because it is very fast, and WGPU was picked because it was portable, which allowed us to run tests on a wide variety of hardware. what are we comparing ourselves against? We're comparing against the light field stereoscope. In many ways, the light field stereoscope is very similar to our very first approach. It has a similar update rule. The only difference is instead of taking the target content, this 2D target content, and some kind of mapping matrix, it takes a vector L, which is the sampling of the light field, right? And this actually will prove to be very important later on. From this, we built two different pipelines, one for the separable approach and one for the stereo approach. The advantage of the separable approach, as I said, is that the sampling is a lot faster because given an image and a number of viewpoints, we only need to sample a row and a column times the number of viewpoints. Whereas the stereoscopic approach has to sample as many viewpoints and of course, at least every pixel in the target image, if not more. So much lower. What does that give us in terms of results? What are the key takeaways now that you've seen the architecture and the types of experiments? So the first thing is the tensor representation is very fast, right? It's a 10x improvement compared to the pure matrix representation. It's sometimes even better, right? Next, the sampling time, as promised, is much, much lower on the separable approach, right? As you increase the amount of rays or increase the number of observers. So here, for instance, we go from one observer to one observer plus kernel to two observers plus kernel, right? That's kind of what the lines are. And you can see that the stereo approach, every observer or every kernel, makes us go up, whereas the stereoscopic, the separable approach remains on the ground. Next, let's look at the runtime, the time to generate that image from the sample data. So surprisingly enough, when there's only one observer, the stereoscopic approach does better. But as soon as we introduce a kernel, the stereoscopic approach shoots up, whereas the kernel for us is practically free. So I dug a little bit deeper into why is that. And the reason is there's two different operations actually happening here. The factorization time, the time to do all of this math, and the build time, the time that it takes to retrieve the data and run and build the factorization. And what we notice is that the build time is really high for the stereoscopic approach and this has to do with our mixed implementation of shipping information back from the GPU to the CPU. So diving a little bit more into why factorization is slower but runtime is faster, what we notice is that the L representation very quickly grows with the amount of observers, whereas the amount of data we have to push is much lower, right? Now, we are paying, the trade-off we're paying is that we have to do more compute, right? You'll notice here that the amount of mflops is about twice as high, but we're still better on runtime, right? So looking at all these results, I went ahead and ran this for many more configurations. What's important to note is that the first observer is practically free. So going from the red, which is the separable approach, to the green approach, green, which is the kernel, the addition of the kernel to the separable approach, you'll notice that we pay practically no cost, right? And apart from the largest target size and the largest panel size, we tend to run better. This leads to an interesting question, which is target size and panel size. What's the relation? What makes the best image, right? Because under the hood, this is actually a discussion on DPI. If you have a high target resolution but a low panel resolution, you'll get these kind of low res images. If you have a low target resolution but a high panel resolution, you'll get this weird, I called it aliasing, but you'll get undersampling as pixels that should have been sampled aren't, right? So in order to understand this more, I ran a couple of experiments using DSSIM, which I forgot to put the D here, but the objective lower is better, right? So we're trying to notice the discrepancy between the ideal image and the images that are produced. And what you'll notice is that movement in either axis does not guarantee a better image, right? So it's likely that, and I've got some more panels, but I use this one to illustrate. It's likely that this is more scene dependent than and there's no general rules. So what are some conclusions? What are some things that can be taken away? So the first is, let's talk about threads to validity, right? Right now, Fire does sparse matrices single-threaded. What would happen if you were to multi-thread the code? Well, using Amdahl's law, we would actually expect our computations to perform even better. And the reason for this is you can't multi-thread the transfer of the data, but you can definitely multi-thread the matrix multiplication, right? So we would expect the discrepancy to get even greater. But of course, that's just on the CPU. What happens if we were to move to the GPU? So if we assume that the GPU completely removes this build time, right, and you use some effective buffer or remappings and stuff, what's interesting is that the sampling time is already accelerated, right? So neither approach can go under its sampling time. And stereo is hard limited to 1 millisecond, as that is their sampling time, whereas our sampling time is in the nanoseconds, right? So the question becomes one of what is the exact acceleration factor, right? I've seen various claims in the literature on how much you can accelerate sparse matrix multiplication, and yeah, this is still open, right? This is still a legitimate criticism. So what could be future work? The first is applying this to applications. I already talked about GPU acceleration, but another that I think is more interesting is this idea of a client-server architecture, right? We started this whole conversation with this idea of we want to figure out a way to do 2D AR on the cheap and as nicely as possible. Because the data is so low, a possible application is one in which we have a lightweight VR headset that has sensors on board in order to, do eye tracking and all this stuff. Sends that data over to some powerful computer, and then receives the images that it needs to display. Right? Networking times have gotten good enough that this kind of real-time streaming is definitely possible. The next is looking more at hardware, right? So this was not tested on real hardware. There's plenty of complications. For instance, transmittance rate of even the best OLED panels is still like 64, 70%. And therefore that would add complications. The other thing is we did not consider any kind of optics, right? The original stereoscopic paper considered optics, and that would be probably really interesting. Then there's some future work to be done at the theory level, right? So obviously this is something that everybody says when they're dealing with these kind of problems. Oh, if somebody finds a closed form solution, you could be much faster, but it's true. Lastly, we made a very important decision at the start to immediately focus on discrete space, right? Continuous space might offer a different approach, might offer different trade-offs, and might be well worth investigating, but we did not have the time for that. So thank you for sitting through the presentation, and I leave the floor open to questions.
Okay, great, great presentation. Thank you very much. And I'll ask one first question, then I pass on to Rafael. And then there's also a question from the audience. So
wonderful.
Perhaps what I'm going to do is like I'm going to do one question and show the question from the audience that's related to another question. Then Rafael takes on. So my first question is that you just finished your master and at TU Delft, and then have you already published your work or planning to publish, or how are your plans academically?
I'm going to be completely honest. I have no plans at the moment. I am, if if Ricardo believes there is something to be published here, I would be more than happy to contribute to that. But my job started 2 days after the defense, so it's been a little bit hectic in that regard. I also think you probably would have to clean some things up. The thesis itself is, and I say this as kindly as I can to myself, very poorly written.
Well, actually, like if you send us the link for your thesis, the PDF, I can put on the page of the talk, and then people, then when are curious, they could take a look to get more details and everything.
All right, absolutely.
So
I can send that to you. I can send that to you.
Oh, that would be great. So, and then I'm going to put here this question from João Paulo. And it's actually sort of you already more or less answered because because you put this before your last slide. So in the last slides you said that you didn't actually apply this to a concrete light field display. But if I could take has two parts, right? Because one is saying that what would be the architecture that you would use, and then and what would take that, and I kind of complement, because Rafael told me that before starting this project, you worked on a company that has a very nice light field display that in a way inspired the project. So if you could kind of discuss all these issues together, and then pass to Rafael.
Absolutely. I think I'm going to take this opportunity to talk about two things. The first is, how could you extend this to the real world, right? And I think that, let me see if I can go back to the math. So when we're doing this tensor decomposition and etc., it should not be too difficult to add some kind of constant factor to take into account the transmittance of the physical panels you're working with, right? I left that question kind of open, hoping that by the end we'd have enough time to test on real hardware, but unfortunately that wasn't the case. But if I had to test it on real hardware, this is where I would look, right? This idea of putting some kind of dampening factor on the multiplication to represent the fact that even if both panels are perfectly clear, they will still appear somewhat dark. As for what kind of hardware setup, the company Video Window primarily did things with LCDs, but from what I've read in the literature, the way to go is actually with OLED, because you'll be able to get a much higher transmittance rate. How to set this up, all of that, I'm not a hardware engineer or an electrical engineer, so I would leave that to more qualified people. But I do think a real world test would be a real test of quality.
I see. Yeah. So I guess that gives the cue to Rafael, because Rafael talked to me about your work, and then he was mentioned this thing of like the continuous discrete and things like that. So maybe Rafael wants to explore that point or some other point.
Well, definitely, if you model things differently, we would reach, as George said, different trade-offs of quality and computation time. But I think it's very interesting in regards to what George presented to us today, his concern with the implementation, right, using Rust and WGPU. And while this modeling for, if it's a continuous space, is more theoretical, and we need to follow this path for a while to reach some more plausible conclusions, because there is certain challenges around modeling things continuously, because the computer can usually represent things continuously unless you have like a function or a model, a mathematical model like that. But a question that I have for George is about when he produces the contents. So, for example, when he compares the stereoscope implementation to the implementation that exploits separability, what information is coming from the CPU side and what is produced already on the GPU side? Because if you're dealing with a synthetic scene, maybe everything comes from the GPU. You never have to make this communication between CPU and GPU when your scene is already in the GPU, you're sampling in the GPU, you're processing in the GPU, which might be related to perhaps the overhead that you mentioned related to the stereoscopic implementation, if I understood it right. So do you have something to say about that?
Yeah, absolutely. So if I understand correctly, you're asking about kind of what's the work split, and would it be possible to do all of this in the GPU, given that this is a synthetic example, right? Like the scenes I ran this on are all rendered, right? I did not. I don't know. I don't have a headset to test this on, etc. Right? Is that correct? Am I?
Yeah, but I mean, in a more complex scene, you could have pre-sample the scene and save, like, because light fields are very heavy due to the high dimensionality. So you could sample your scene in a pre-processing stage and save it on your hard drive, and then you have to deal with the communication between the storage to the GPU, while sampling on the fly gets rid of this communication between CPU and GPU. But then you have to sample on the fly, right?
We sample on the fly and we don't store anything in files, right? So all of this fits in memory. What happens is we have a scene that gets rendered, obviously, right? But we continuously we can continuously sample that scene and send back buffers of shared memory between GPU and CPU. Which then the CPU has to like unpack, because what the GPU is sending back is essentially just a vector of U8s, right? The CPU is not familiar with the structures, so that's what the build time is. It's the time taken it's how much data is getting pushed from one side to the other. You can definitely pre-sample the scene, but and actually this brings me to another thing I forgot to mention that's really interesting. Because we generate our light, because we kind of take our light field with us, right? Because we generate our light field from the target content. If you want to maintain the same scene but change the target content, you don't have to sample again. So for instance, for 2D animated content, right, all you have to do is recompute this update function and change RT to include the new image, instead of having to redo resample L and redo the factorization, right? So I would argue that right now the way we're targeting this is on the fly sampling of the scene and generation of the factorization of
okay. And just one curiosity, how much VRAM did you use during your experiments?
So the VRAM usage for our method is under 1 gigabyte. And the VRAM usage for the stereoscope method is was the max that I could get on my GPU, which is 4. So that also once again shows that when I was here you can see that the amount of rays per dimension that I tested up to was up to 6,000, right? When we go to this graph, you see that I had to drop it to 2,000 because when I introduced multiple observers with the stereoscopic approach, or with the stereoscopic approach, I ran out of VRAM when we got to 4,000 rays. Whereas this approach can go all the way up to 12,000 rays, 15,000 rays, 18,000 rays, right? Because at the end of the day, all we're passing back is a relatively small vector. So
okay.
I hope that answers the question.
Sure.
Yeah, no, great. Okay, so we don't have more questions from the audience, but people like it, the talk a lot. Thiago is kind of cheering up, saying that it was great, and I concur. And then I guess if you have no more questions, you can kind of close now. And then I'd like to once again thank George for taking the time to show this his work to us. And then we are actually working on actively in this area of light fields, planar functions, displays, and that's going to kind of inspire our research here.
Well, I thank you. I'm honored to present. When Rafael reached out to me, I was over the moon.
Okay, great. Yes. So I'll close the presentation now, and then we keep in touch.
Yeah, absolutely.
Okay, great. So when the transmission.